All right, everyone. So this is lab 4, where we will be exploring the Newtonian dynamics, meaning that we're going to be looking at objects' motion due to forces acting on it. So the concept of force came to us from Galileo and Isaac Newton, where Isaac Newton was able to put together 3 laws of motion to describe, um, let's say, what we call this concept of force and what happens to the object when the forces acting on it, when the forces balance each other, when they are not balanced. That means those are the things we're going to be exploring in this chapter. So concept of force, if you can think of it, is nothing but some kind of push or pull. And this push or pull is due to a number of things. Technically, it can be a person pushing, it can be gravity acting on the object, it can be something being pulled by a string. Anything that has some kind of push or pull effect is considered to be a force. So for example, let's say you have an object, there's on a flat surface. If this object is sitting there on the flat surface, let's say, I don't know, a ball, think of like a tennis ball or a, maybe like ping pong balls or something like that. If you have it sitting on the ground like this, without moving, doesn't necessarily mean there are no forces acting on it. So even an object at rest has 2 forces acting on it, and those forces are, one of them always gravity, because gravity is one force that's always acting, and the other one is normal force, which comes from the surface. That means the idea of force is best described with what we call a net force. So let's write it like that, F net. So this concept of F net means that you have object where several what we call agents can be pushing or pulling. So this is our object. Object is basically the whatever we are looking at that being pushed or pulled. And then we have agents. So agents are maybe people who push or pull, or could be, let's say, earth who's doing the pulling, or could be the surface that prevents, for example, objects from falling even further toward earth. So the idea here, agents are whoever exerts force. So for example, right, so at this point, if there's a box, that's my object. If there's a person pushing the box, that's the agent. So agent, and this is the object. Object is being pushed by the agent. It's just easier to categorize anything or anyone who's exerting force as agents, and you have then one object of interest that you look at in terms of what happens to the motion of that object when multiple agents acting, and exerting force. All right, so let's go back to just having the ball on the ground. Now, if it's just sitting there, what means that there right now 2 forces acting on it. We don't see them, we don't see anything pushing or pulling, but there's one always acting on it, that's the gravity. So let's put like F of G. F is what we use for the force, general notation for the force. G means that gravitational force. The subscripts a lot of times, help you put something in perspective. So say gravity is pulling things down. But if you have a ball sitting on the ground, you don't see it falling to the ground. Like you don't see it falling through the ground. The reason, because surface itself exerts force in opposite direction. That means I can say that there's a force acting from the surface in the opposite direction. And that force is known as a normal force. So normal force. Normal generally means perpendicular. So that means, see, this is the perpendicular to the surface. And normal force is always perpendicular to the surface. Perpendicular just means 90 degrees relative to the surface. Now, what I have then, this net force is going to be equals to then gravitational force and a net force together, a normal force together. But what I have here is I have net force plus then gravitational force, but forces are vectors. So forces are what we call vectors. And vector is a directional quantity. Meaning that if you take one direction to be positive, in this case, for example, I'm going to say, all right, so up is positive. I'm going to be positive vertical direction. Any force that is up it's positive. So in this case, normal force is positive. Any force that is down is negative. In this case, gravity is negative. That means this becomes technically normal force minus gravitational force. That means this guy here is negative. So we need to subtract. And if you have an F net where normal force minus gravitational force and you see objects not moving, that means those two cancel each other. That means they have the same strength. That's why the object is not moving. Because when F net is equals to 0, this is what we call, balanced forces. So those are balanced forces, meaning that object will be in what we call equilibrium. So balanced forces, so object is in equilibrium. Okay, so we're going to look at balanced and unbalanced forces. Now, we can make this object move, for example, if we put it on an incline. Let's say, if I put some kind of incline, let me imagine if I have, and I'm going to have you guys do this at home. So you put a couple of books like this together and put some kind of board like this to create an incline and put then the ball right here. And you're going to see that this ball is no longer going to stay here, at rest. It's going to start sliding down, okay, or rolling down, because it's, circular, it's kind of like, spherical, it's going to roll down. For us, we can just ignore that rolling. We can just say it's just equivalent almost to sliding. The idea here is that when it starts going down, you still have the same two forces acting on it, actually. You still have a gravity acting downward direction. This is F of G. But normal force in this case now act perpendicular to the surface. So this is in this direction. Okay. Which means that at this point, they are not exactly in the opposite directions. So the gravity has ability to, in this case, to have the object slide down. And that's kind of what we have. That means this object is now going to start rolling down and it's going to start speeding up because of the gravity. Because normal force, see, when they are exactly in opposite direction, have the same strength, they cancel each other directly. Here, I can no longer say N minus F of G. This doesn't work because they're not on the same, let's say on the same axis anymore. In this particular case, then this normal force, which is the force from the surface, is not able to cancel the gravitational force, and it's unbalanced, and the system then starts, accelerating down. That means now we're dealing with unbalanced forces. Okay, that means there are different types of force, right? As I said, normal is a surface force. And there's another surface force that we have, and it's the friction. So for example, if you take in the agent to be a surface, what we have two forces that surface gives us. One is normal. Let's say normal. And the other one is friction. So for example, if you have an object on the ground, this normal force always acting perpendicular to the surface. There's a normal force. And this arrow just gives me the direction of that. Friction always acting such that it's either to the right, to the left, or to the right. I'm going to talk about that a little bit, but the normal force, the friction force, imagine, right? So this is perpendicular. This is always parallel to the surface. Perpendicular, normal force is always perpendicular to the surface. Friction always parallel to the surface. Okay, so in this case, if the surface is smooth, we can say that there is no friction force. But even if there is a friction force, it's going to be acting in this direction, because friction always acts in opposite directions. It's always parallel to the surface, but always acts in the opposite direction of the motion. That means it's going to acting in this direction. So that's why, for example, what I have here is if object going down, friction going to be acting in opposite direction, so toward the top of the incline. Okay, so this is one of the experiments you're going to be doing. There's also, let's say, if the agent is, let's say these are agents, right? If agent is Earth, then what you get here is you get gravitational force. So gravitational force, and the gravitational force always acting straight down toward Earth. Okay. You can also have, for example, the agent can be some kind of rope or a string, rope. Usually from this, you get tension force. Okay, so for example, if you have a box and then you wrap around tension, the string, and then somebody's pulling by that string, that means that force, we say that that's a tension force, and given with a T, capital T, that's for the tension force. So this is, let's say, F of G. This is friction force, lowercase f, and this is normal force. All right, so the idea here in this lab, we're going to be talking about how object being pushed or pulled along the horizontal axis going to move depending on the net force. So what we have here, we have balanced forces. So technically, balanced forces represent Newton's first law. Which simply put, if object is at rest, let's say if object is at rest right now, it's going to continue staying at rest as long as the net force is zero, which means that forces are balanced. For example, remember, if I have gravity acting down and if I have normal force acting up, and they both exactly same, so in a y direction, what I can say that normal force, or I can say it like this, right? My F net in a y direction equals normal force minus F of G equals 0. They cancel each other. So just box is just sitting there. That means you see anything around you just at the rest, just on the ground, there are two forces acting on it. Gravity down, normal force up, but they're balanced, so it's 0. So the Newton's first law basically tells you that if object is at rest, it's going to remain at rest as long as forces cancel each other. Same thing we can do, for example, let's say here's a person pushing this box. Let's say the person decides to push this box. That means I can say that there is this force in this direction. So this agent now, this person, so it gives me a force 1, let's say. There's a force 1 acting to the right. Okay. If I have just this force, the object is going to start accelerating to the right. But we're talking about Newton's first law. That means the forces might be balanced. That means there's also has to be balanced in the x direction. So there could be maybe, let's say, the friction. Friction then will be maybe acting in opposite direction. So this is a friction. And imagine you try to go right now and push your refrigerator. You're going to push it, but it's very heavy, so it's not going to move at all. That's because there's a lot of friction between the refrigerator and the ground. So then this F net in the x direction is then force that you apply. Let's say, let me put like F of A, applied force. Then minus the force that is you get from the friction. Usually we write lowercase f for the friction. Again, they cancel each other, which means, for example, if this is 10, this is then also 10, but because it's to the left, this direction is negative 10. So you can see, right? 10 minus 10, you get 0. And the units for the newtons, the force is newtons. So after obviously I have Isaac Newton. So 10 newtons minus 10 newtons, you get 0. So that means this is balanced. When you push something else, some other agent pushes in the opposite direction, and your system is in balance. Okay, that means they all cancel each other. How about if your system is unbalanced? Okay, so unbalanced, then we are looking at the Newton's second law domain. Okay, so Newton's second law. Well, Newton's second law tells us this. If you have an object at rest, let's say here's the object. If you apply a force, so let's say here's somebody, starts pushing the box. That means this person exerts force. Let's say force, let's say 5 newtons. So pushing it to the right with 5 newtons. Well, if this is no friction surface, that means this is very, very smooth surface, then there is no other forces to balance this applied force. Then what I have here is in the x direction, then there's only applied force and nothing. So let's say minus 0, right? Nothing to cancel it. That means now my F net is not 0 anymore. How about in a y direction? So for example, in a y direction, I might still have a gravity and I might still have a normal force. That means in a y direction, I can still have normal force minus f of g equals 0. It's balanced in the y direction, but it's not in the x direction. Then what is this equals to? Well, according to the second law, F net equals to mass times acceleration if you have unbalanced forces. That means this is equals to mass times acceleration. That means acceleration, remember, is objects change in motion. Now, what we're saying here is that object changes its motion because there is a force, non-zero force, unbalanced force in a certain direction. That means what I can say here is this is equivalent to having 5 newtons equals mass times acceleration. So for example, if I know the mass of the object to be, I don't know, let's say 2 kilograms, for example, then I can solve this for acceleration. I can say in x direction, what I have is that, remember, it's applied force equals mass times acceleration, which this equation itself is known as a Newton's second law. Then acceleration, divide both sides by mass, is force over mass. In this case, 5 newtons divided by 2 kilograms, then I get 2.5 meter per second squared. You can see that how I can find this acceleration. Okay. Now, this is then Newton's second law, means that if you have non-zero force in one of the direction, in this case, horizontal direction, your acceleration in that direction based on how much force you have. So that's why this equation always works. A equals applied force divided net force over mass. That means, for example, here when I come and say my acceleration equals net force over mass, see my net force is 0 in x direction and in a y direction. So I can say my net force is 0 divided by mass, I'm going to get 0. That's why there was no acceleration, because net force was 0. Here I have acceleration because net force is not 0. All right, so what if we have other forces in the horizontal direction? Let's look at it. So let's say there was additional force. Let's say there was this, let's say a friction, and it's acting in this direction. But let's say the friction is only 2 newtons in a negative direction. So it's less than how much you're pushing. Well, in that case, what I will have in x direction, at least, I'm going to have then applied force, positive to the right, minus friction, it's negative because it's to the left, equals, then I'm going to do my F net. So then this is going to be 5 newtons minus 2 newtons. Now what I get only 3 newtons. That means when you push 5 newtons to the right, but the friction, acted to the left of 2 newtons, that means the net effect is only 3 newtons. But still, then I can say that F net equals mass times acceleration. So then acceleration equals, divide both sides by mass, then it's F net over mass. But now I have only 3 newtons of F net, but still same 2 kilogram object. So the idea here is, in this case, I have only 1.5 meter per second square acceleration. That's because my forces, in a way, like let's say acting in the opposite direction, so the friction cancels out some of the effect of the push force. Okay, cancels out some of the effect of the push force. But generally, this is the whole idea of this particular lab, looking at balanced and unbalanced. When your system is balanced, that means your system going to do this. It's going to be in equilibrium. So, and in equilibrium, you have 2 conditions. One, if the object is at rest, something like this, condition 1. If at rest, then will remain at rest. If at rest, will remain at rest. Condition 2, if moving, will continue move same speed. That means it's not going to speed up or slow down, because what we're saying, there's no acceleration. And remember, acceleration is what makes you speed up or slow down. As long as your forces are balanced, if the object is at rest, it will remain at rest. If object is moving, it's going to move with the same speed, same direction, without changing its velocity. That's what balanced forces do. Unbalanced forces, well, they change the velocity because now there is acceleration. Okay. Let's look at the lab itself. So the experiment on Pivot Interactives basically looks at exactly that. So let me. Okay, so you can see, right? So in this activity, you will explore how balanced and unbalanced forces affect the motion of an object. And we're going to be using a simulation, which is a really nice simulation that's going to help us to kind of see balanced and unbalanced forces. So first, we have a part where we're going to have a ball moving down a ramp. And as I said, right, so it's something that hopefully you guys can do at home. Just grab something, like two books together, some kind of like a board, right? And just create, something similar to this. Okay, it can be anything. You can just improvise, but you have some kind of object. Let's say a baseball, tennis ball, golf ball, marble, right? Something going down an incline like that. And the idea is to look at, if it's going to, speed up or slow down, and what are the forces acting, and due to what force is going to go down. Kind of, mention that in a lecture. All right, so that means this first part, just basically do this experiment and write down your results as a multiple choice questions. Be careful, we had 3 submissions. That means the idea is that you try 3 times until you get it right, and if you get it wrong first couple of times, at least you will learn. So from here, then we're going to go to the, our next experiment. You can see, right? So basically, you do this experiment, and then you answer some of the question based on what you see. Okay. Then you log your answers, and you continue into pushing crate with the friction. In this lab, you're going to launch a simulation. It's a really nice simulation, kind of gives you, let's say, you can see, right? You have a person and the box. So this is the agent, right? The person, or the model is the agent. And then you have the boxes down. So it says, let's explore what happens when a person pushes crate when there is friction between the crate and the ground. Okay, and you can see, right? So here's the, let's say how we can change the friction. So no friction, and this is friction. So when there's a friction, we want to just, let's say you can see, right? Here you have the force. If you want force acting to the right, see, we're pushing, but nothing happens. The idea here is that if you put, the friction between the, the crate and the ground has some kind of maximum value. And the idea is that just like a refrigerator, right? If you give it a little bit of push, it's not going to move. Give it a little bit more push, it might not move. A little push, it might not move. But eventually when you push, you will overcome that, and then it will start then moving. So you can see, right? What I have here is, you can see that the force that will make this move. So if we kind of stop here, see, for example, 85 newtons. If I apply 85 newtons, you can see the sum of forces equals 0, which is the net force. That means this friction force can adjust itself to match my applied force all the way until 213, 20, 26, let's see. See, 250. That means as soon as I apply more than certain value, right? Then it's, but now if I already make it move, it's just going to be, motion. Look at the speed. See, it's increasing because I'm making it, speed up. Okay. All right. So here you're going to learn about that. So it says, you can reset. Here I have to reset, and then you're going to be using, let's say, now push with 100 newtons. What happens? Then try to find the forces are created unbalanced. You're going to say, like, if you put 100 newtons, is it balanced or not? What are the ways you can figure out if it's balanced or not? Remember, we talked about, right? So if it's balanced, if it's at rest, and if it's balanced, it's not going to be moving. So is it moving or not when it's 100? And what are the forces? What is the net force? And so on and so forth. And when you do 300, what happens? So those are the things that you can do with that, and write down some of the, and it kind of give you like a picture and, what to do and so on and so forth. So this is pretty much following the instruction, direction, and getting, let's say, playing with that simulation and see what's happening over there. Then again, you then will go and answer questions based on what you see, the observation. Again, you have 3 submissions. So don't get discouraged if you get, the first time wrong. You have another one and another one. So you can net up to 3 times to get it right. You're going to log the answer, and then you're going to do the next one. And this one, you're going to push without friction. That means if you go back, remember, friction, no friction. If this goes to no friction. So see, a little bit of force is already making it accelerate, right? So that means even if just a tiny force is going to make it accelerate, because there's nothing to prevent, right? You have only one force and nothing to balance. Okay. That means, this part basically just what happens if you do 100 newtons and so on and so forth. So basically exploring the motion when there is no friction. That means nothing else trying to balance your applied force. Okay, so do the experiment, then write down your observations. Putting all together, kind of summarize where you have a balanced, where you have non-balanced, and then here, always like, we have a refrigerator that coming to play. So let's say give you some scenarios, which one of them is let's say the balance, which one of them is not balanced. So you kind of get to apply what you just learned from the experiment, from the simulation, answering this last couple of questions. Should be straightforward. So if you have any questions, let me know. Come to my office hours and get help. But should be straightforward, and I think should be pretty fun to work with this lab.